Hello everyone. Let's discuss the second chapter of unit number 3, equilibrium of beams. First of all, we need to discuss certain basics of equilibrium of beams before we solve any numericals. Beams is a horizontal structure which can bear loads applied on it, and the structure of the beam itself will be supported. So the basic function of a beam is to bear loads, to hold loads and to remain steady. So beam has to be in equilibrium. It will not break, or it will not move, or it will not bend. What are the different type of supports given for a beam? The first type of support is simple support, where the beam will be simply kept on a surface. For example, let's say on a wall, a beam, the one end of the beam is just kept. The wall can be considered as a simple support. Simple support always gives a single reaction which is always perpendicular to the surface. In case of second type of support, which is roller, these are the symbols to show a roller support. Also, we will have a single reaction always perpendicular to the supporting plane. So the surface on which roller is kept, to that surface the reaction is always going to remain perpendicular. For example, here now I have shown one roller kept on a horizontal surface, which is the roller is supporting end A of one beam. So the reaction exerted by this roller on the end A of the beam is a single reaction which is perpendicular to the surface. So the surface on which roller is kept is horizontal, so reaction has become vertical. So here we have shown that reaction RA, which is the reaction exerted by the roller on the end A. Here we have got roller placed on one inclined surface, whereas the surface makes angle theta with horizontal. Reaction remains perpendicular to the surface, that makes angle 90 minus theta made by the reaction RA with horizontal. So remember, whatever will be the inclination of the supporting plane with horizontal for the given roller, angle made by the supporting reaction is going to be 90 minus theta. Okay, moving to the next type of support, which is hinge, or let's say pin support. It is also called a pin support. Generally, the symbol for hinge or pin is something like this: a triangle kept on a surface, or let's say this particular symbol kept on a surface. We are not showing any rollers here. We are not showing such circles in the symbol of hinge. Hinge support has two reactions, horizontal as well as vertical. So the directions of these two reactions are always fixed. One will be horizontal and the other will be always vertical. The horizontal direction is generally assumed to be x direction, and vertical is assumed to be y. That's why we generally name these reactions as ax and ay. If the end A of the beam is supported, then the reactions will be ax and ay. Here we have mentioned one very specific thing. It doesn't matter whatever is the inclination of the surface on which the hinge is kept. Irrespective of that inclination, the reactions are always going to remain horizontal and vertical only. See, here I have shown one hinge kept on the horizontal surface, and in that case we have two reactions, one horizontal and one vertical. Here we have shown a hinge supported by a vertical surface, but still here also we are going to have one horizontal and one vertical reaction. Not only that, even if we place a hinge on inclined surface, there also the reactions exerted on the hinge are always going to be one horizontal and one vertical. Now actually we don't know whether the horizontal component will be going in the right direction or left direction. The vertical component will be going in the upward direction or downward direction before we solve any numerical. So when we are going to solve numericals, at the end, when we are going to have answers for ax and ay, there we can decide whether our assumed directions are correct or not. How, that we will discuss while solving the numerical itself. So here again, one important thing we have to note that whatever directions we are showing here for the hinge reactions are going to be assumed directions. Further, the next type of support for a beam is a fixed support. Now, a fixed support is going to have always three components: one horizontal, vertical, and third one will be a moment. Moment is nothing but rotation. So if one end of a beam is, let's say, buried, is fixed in a surface, or let's say in a wall, so in that case we are going to have three reactions: ax horizontal, ay vertical, and one moment. Either the moment is going to be clockwise or anti-clockwise. Again, we have to assume some rotational sense for this moment. It will be confirmed whether our assumed direction is assumed rotation is correct or not at the end of our solution. Fine. So these are the more frequently used supports, or the kind of supports which will be involved in our numericals. There are several others, we need not discuss those right now. We said the function of a beam is to take loads. We have to apply loads on the beam, and the structure of the beam has to remain steady, or it has to remain in equilibrium. So what are the different type of loads we can apply on the beam? Let's see those. The first one is point load or concentrated load. As the name suggests, the load, now load is nothing but a force only. If we are applying a force on a structure, generally it is called a load. So here we have shown three loads which are applied at single specific known points over the length of a beam. That's why these are called point or concentrated loads. Their effect is concentrated at a single specific point. So these are called concentrated loads. All three, F1, F2 and F3, these are three individual point loads here. The second type is uniformly distributed load, UDL. It is also called a rectangular load because the shape of the loading appears a rectangle. This is another way in which the uniformly distributed load can be shown. This symbol also represents a uniformly distributed load only. Let's say a uniformly distributed load has a span of L and it has intensity W. Remember, intensity is always mentioned in kilonewton per meter. That means how much magnitude of the force is distributed per meter length of the given span. So in that case, if we have to convert in our numericals, we will have to convert the given uniformly distributed load into its equivalent point load. That means if we remove all these point loads, if you remove the entire band of this loading, and instead of that you have to just show a single point load, so that is called equivalent point load. So if you have to convert a UDL into equivalent point load, you have to find out area of this rectangle. So length into breadth, that is the area of the rectangle. In case of UDL, length is nothing but the span on which the load is distributed, and the breadth is nothing but the intensity of this loading. So W into L becomes the magnitude of the point load. We know that for a rectangle, the position of the centroid is located exactly at the half length, right? So here also the magnitude of the point load is located exactly on the half length of the span. So whatever is the length over which the UDL was distributed, exactly on the midpoint of that, that is from either ends at distance L by 2, the point load should be located. And this will be a single point load which is measured in either Newton or kilonewton. Whatever was the unit of intensity, according to that we can give the unit for the magnitude of this point load. So we'll just recap. Whatever is the magnitude of the equivalent point load which we have to get from the given UDL is nothing but area of the rectangle. So W into L, that is intensity into the span, is the area of rectangle which represents the equivalent point load for the given UDL. The next type of loading is called uniformly varying load. So here the uniformly varying load is also called as a triangular load because the shape of the loading is appearing as a triangle, a right angle triangle to be more precise. If L is the span and let's say W is the maximum intensity at one end, the intensity goes on varying. That means changing uniformly. It goes on decreasing continuously, and at one end it becomes zero. Right? So this is the right angle triangle formed by the loading, and it can be converted into its equivalent point load in this manner, where the magnitude of the equivalent point load representing this UVL is nothing but area of the triangle. We know area of the triangle is half into base into height. So here base is nothing but the span, that is length L over which the load was distributed, and the height of the right angle triangle is nothing but the intensity W. So half into W into L will become a single point load which we have to replace for this UVL. Where it should get applied on the total length L, at which exact point? So for that we need to know what is the centroidal position for the given right angle triangle. If let's say base B of the given right angle triangle is, in that case we know that from the right angled edge at distance B by 3 we find the position of the centroid. In the same manner, wherever we have the maximum intensity, or let's say the right angle formed in the given triangular load, from that right angled edge at distance L by 3 we have to locate the equivalent point load. So this is how the placement of the equivalent point load representing UVL is given while we convert the UVL into its equivalent point load. Further, we can have a specific type of loading which is called trapezium or trapezoidal loading, where it is just a combination of uniformly distributed load and uniformly varying load. Uniformly distributed load is nothing but a rectangle, and the other is triangular load. The UVL is triangular load. So we have a trapezium. This is a trapezium, and we are given this trapezium with at one end intensity is W1 and at the other end the intensity is W2. Here the intensity is reducing uniformly, but it has not become zero at the end A. There some intensity W2 is still present. Otherwise it can be directly a triangular load, but here it is not a triangular, it is a trapezium load. So how to convert this trapezium load into its equivalent point load? For that we have to just distribute this trapezium into two shapes, one a rectangle at the base and then remaining is the right angle triangle at the top. So if you separate these two shapes, the height of the rectangle is nothing but the intensity W2, which is here, where the length of the rectangle is L. Same is the length of the given right angle triangle. Let's say length or the base. The base of the right angle triangle remains the same as that of L, and the intensity or the height, the remaining height of the given triangle is going to be the total height W1 minus the height W2. So W1 minus W2 gives you the height of the triangle only, and that is the intensity of the UVL, uniformly varying load, W1 minus W2. Now we have split a trapezium into two shapes. One is the rectangle and the other is the right angle triangle. So now we have to convert both into their corresponding equivalent point loads, and we have already discussed this, how to convert it. The rectangular uniformly distributed load has to be converted into its point load by calculating area of the rectangle, which is W2 into L, and it should be located exactly on the midpoint of the length AB. So here I have shown a little bit longer length of the beam AB just for the sake of convenience for understanding all the dimensions and all. So exactly on the midpoint of the length AB on which the entire trapezium was distributed, we have located the equivalent point load of the rectangle at L by 2 from either ends, and for the given triangle only, from the right angle triangle side, from the right angle triangle corner, let's say we have located the point load at distance L by 3. Area of the rectangle is the magnitude of the point load for the UDL, W2 into L, whereas whatever is the area of the remaining right angle triangle will be magnitude of the point load. So here the base is nothing but L, height of the triangle is W2 minus W1. So half into W1 minus W2 into L. These many newtons will be the magnitude of the point load for a given right angle triangle. So remember, if you have a trapezium load or a trapezoidal load, in that case you will have to convert it into one rectangle and one triangle, and then for each shape you will have one equivalent point load respectively. So trapezium load is going to get converted into 2 point loads, remember. Fine. We'll solve some numericals in which this trapezoidal load will be involved, and we'll have to convert the trapezium into point loads. In that case, we will see these calculations. Moving further, let's see what are the different type of beams. Now, mainly the type of beams are decided based on what kind of support they are having. If a beam has both the supports, simple supports, in that case it is called a simply supported beam. It's a very simple consideration. If a beam has rollers at both the ends, it will be called a roller support. If a beam has hinges or pins at both the ends, it will be called a hinge supported or pin supported beam. If both ends of the beam is fixed, if both ends of the beam are fixed, in that case such beam is called a fixed beam. Of course, for a fixed end we know there should be 3 reactions, horizontal, vertical and one moment. So if we have both the ends of the given beam fixed, we are going to have in all total 6 reactions, horizontal, vertical and a moment, each at each end. So both ends collectively, total there will be 6 reactions present for a fixed beam. Then there is something called continuous beam. In continuous beam, you may have 2 or more than 2 supports, but all of them they are going to be different. The same support is not going to get repeated, but we are going to have several different type of supports, either 2 or more than 2. For example, let's say here in this beam we have one hinge and one roller. Here we have, in this case, a fixed support, then roller support and one simple support. So if you have different kind of supports present on the same beam, 2 or more than 2, it is called a continuous beam. Further, there is something called cantilever beam. This is another type of beam, and specifically this is a beam where it has only one end fixed and the rest of the length of the beam is not having any kind of support. So if a beam has only one fixed end and no support all over the length, it is considered as a cantilever beam. Further, overhang beam. In overhang beam, necessarily both the supports are going to be simple only. Then what is the difference between simply supported beam and the overhang beam? Here, out of the given 2 simple supports, at least one support should be not present at the end but somewhere on the inner side. At least one support should be present on the inner side of the beam. So here in this example, the first one, in the beam AB, we have one simple support at A and the other simple support is not present at the end B but somewhere on the inner point C of the given beam. So whatever is the remaining, the leftover portion without any support till the end is referred as overhang of the beam. Okay, the entire beam is called overhang beam, but specifically this particular portion of the beam is the overhang part. Likewise, here in this example of the beam, we have 2 simple supports and both are existing on the inner side. Here we had only one support on the inner side, but here we have both the simple supports on the inner side of the beam. So we have got two overhangs in this case. Apart from these types of beams, we can in general classify beam into two different categories. One is simple beam and the other is compound beam. Simple beam is a structure which will have only one beam present in it. It doesn't matter what kind of supports it has, but necessarily it should have only single beam present in it. Whereas in compound beam, if we have two or more beams connected together to form a bigger structure, so two or more beams are connected together with the help of, let's say, internal hinge or rollers, the structure formed is called a compound beam. Of course, we will also be solving numericals where we will have to deal with compound beams. So there we will discuss in more detail what is internal hinge, how two beams can be joined together with the help of a roller, and so on. Right? Moving to the next part further. I think this is the theory portion which we need to know for solving the numericals of beams. So further, I think we can start solving the actual numericals. Let's begin with question number 1, which says determine support reactions of the beam loaded and supported as shown in the figure. Okay, so along with the question, diagram is given in which we can see there is one beam AB. Now the moment we have seen the diagram and we have read the question, we need to identify what kind of supports are present for the given beam. Here we can make out that at point A we have got a hinge support, whereas at point B we have a roller support. And there are certain loadings now present on the given beam. We have 20 kilonewton and 10 kilonewton loads. Apart from that, we have a curved arrow. What does that represent? Either it represents the moment or a moment of couple. So it can be anything. It can be a moment or couple. How can you decide whether it is a moment or a force? If the unit is given kilonewton meter, force multiplied by the distance, definitely it is a moment, or let's say a couple only. It's not a load. Fine. It is a rotation that is present in the system. So now we have to solve this. We have to solve the beam. Generally, whenever we say that we have to solve a beam, that means actually we have to find out the support reactions. We have to support reactions given for the beam. As we identified, at point A we have a hinge and at B we have a roller support. Let's draw the FBD of this beam. If I have to draw FBD of beam, actually I have to remove both the supports, and instead of these supports I have to show the reactions exerted by the support. So let me remove both the supports. At point A we had hinge, so we have removed the hinge, and instead of that now I have to show reactions exerted by the hinge. Remember, hinge exerts always two reactions. One is going to be horizontal and the other is going to be vertical. Because those are applied at point A, let me call those AX and AY. In some cases, or if at all you want, instead of AX, you can also call the horizontal component of this hinge as HA, the horizontal component at point A. And instead of AY, you can also call this vertical component as VA, the vertical component of the hinge applied at point A. Either use AX-AY nomenclature or HA-VA nomenclature. Anything is fine. I frequently use AX and AY. So whatever are the loadings given to us in the question, let's keep those same. I'm just rewriting the information given in the diagram and I'm completing this FBD. At point B, as we can see that there is a roller and it is kept on a horizontal surface. We know roller exerts only single reaction, which is always perpendicular to the surface. So now the surface is horizontal, so reaction must be vertical. Let's call that reaction RB because it is applied at point B. Let's call it RB. We have certain dimensions given to us in the diagram. Let's rewrite those so that our FBD will be complete. 1 meter, 1.2 meter, 1.2 meter and 1 meter. These are the given dimensions. Now let's solve this. Remember, here we have assumed that the given structure of the beam is in equilibrium. This is a non-concurrent force system which is in equilibrium. So we know that for equilibrium of any structure, particularly here in this case for equilibrium of the beam, if it is a non-concurrent force system, we can use conditions of the equilibrium for solving this numerical. What are the conditions? Summation fx0, summation fy0 and summation m equals to 0. We know that wherever in the structure we are going to have a hinge support, we prefer to use the condition of moment summation m equals to 0 at the hinge point. Let's see how it is going to help us. So I'm going to write the first condition of equilibrium, summation m, specifically about the hinge point. I'm going to say it is equals to 0. Remember, we are not finding out how much is the moment. We already know that the moment of the entire system is 0 because the system is in equilibrium. So we are saying summation ma is equals to 0, where as usual anti-clockwise is going to be positive and clockwise is going to be negative. So why we have chosen point A only for calculating, for applying the moment condition? Because we know A is the hinge point. The purpose of the hinge is to rotate only. This is one point, and the other one is when we are going to apply moment about point A, the components of the hinge AX and AY, their moments are going to be 0. So only the unknown RB, the remaining unknown, will get solved. So let's use it. Moment, magnitude of the force multiplied by the perpendicular distance, vertical force multiplied by horizontal distance into 1. We are measuring all the distances from point A. So 20 into 1, the rotational sense caused by 20 kilonewton above point A is going to be clockwise. So that should be taken minus. Here 34 kilonewton meter is already a moment given to us in the diagram. It is represented by a curved arrow. It is a moment, remember, and the curved arrow representing clockwise rotation, and we know that clockwise rotation is negative. So let's write minus 34. Remember, it is already a moment, so you don't have to multiply by any distance. Load will be multiplied by the distance. Moment has to be just added or subtracted based on its rotational sense. Don't multiply this moment by any distance. That is very important. Further, magnitude of the force 10 multiplied by perpendicular distance from point A up to 10. The perpendicular distance is 3.4. The rotation caused by 10 kilonewton is going to be minus clockwise, and RB will have anti-clockwise rotation, and it should be multiplied by the total length from A to B, which is going to be 4.4. The rotation caused by RB about point A is anti-clockwise, and that has to be equals to 0. So let's calculate RB now, which is going to be equals to bringing all these three constant terms on the other side of the equation. 20 plus 34 plus 34 divided by 4.4. Let's check out this answer. 20 plus 68 divided by 4.4. So the answer is 20. All the loads are given to us in kilonewton. So this reaction RB, whatever we have calculated, also has to be in kilonewton only. We have got positive answer for the assumed direction of RB. So our assumption for the direction upward is correct. This is the roller reaction RB, one of the answers. Still we have to find out AX and AY, remember. So now for that we will use the remaining two conditions of equilibrium, namely first summation Fx is equals to 0, where we know if a force is going in the right direction should be taken positive, and if it is going in the left direction it should be taken negative. Remember, while using the conditions of summation Fx0 and summation Fy0, we never multiply by any distances. So then we have AX assumed going in the right direction, and that is the only horizontal component existing in the system. There is no other horizontal force to balance it, to nullify it. So on its own AX has to be 0. If there is no horizontal effect existing in the system, if there is equilibrium, the only horizontal force existing in the system has to be 0. Say here you have applied a single force principle, where for equilibrium, if there is a single force existing in the system, it has to be 0. That is the single force principle. So AX is 0. Actually, when you say AX is 0, that means AX and AY, these are the two components, one is horizontal and the other is vertical. You are going to have resultant of AX and AY single reaction RA. But now out of these two components, one component AX, the horizontal component, has become 0. So that makes our AY component actually equal to the resultant of these two components AX and AY. Let's call that resultant as RA. Okay, so whatever is the magnitude of AY, same is the magnitude of resultant of both these components. I'm talking about only these two components. I'm not considering any other forces. These two components which are perpendicular to each other, for these two components the resultant is going to be RA. And now because AX has become 0, the resultant component at A has to be equal to AY only. Let's find out RA now by using summation Fy equals to 0. This is the third condition of equilibrium we are using for finding out RA, where upward positive and downward negative. Let's see, we have got AY, which we have said is RA going, we have assumed it moving in the upward direction, so let's take it positive, minus 20. Now here we don't have to consider this moment because this is a rotation. We are talking about vertical forces. We are trying to add up all forces which are existing along y-axis. So moment should not be taken there. Same way in summation Fx we didn't consider this moment. 10 kilonewton, which is also going in the downward direction, and RB that we have calculated, which was 20 kilonewton and in the upward direction. So let's take it plus 20, and that total summation Fy has to be equals to 0 because of the equilibrium. So simply here we are getting our RA component, the resultant of the hinge, is going to be equals to 10 kilonewton, and because it is positive, whatever direction of AY or RA we have taken is correct. So these are the answers. So here in general you can remember that even though if you have a hinge support, and we know that hinge has always two reactions, horizontal and vertical, but suppose in a structure of a beam, if apart from the hinge reaction there is no other horizontal force existing in the system, the horizontal component of the hinge is going to become 0, and we are going to have only vertical component for the hinge present in the system. Let me repeat, if in the structure of the beam, apart from the horizontal component of the hinge, if we don't have any horizontal force or any inclined force in the system, the horizontal component of the hinge is always going to become 0, and the resultant of the hinge is always going to be equals to the vertical component of the hinge. So that we will keep in mind all the time, and because in most of the cases just by observation we can say that AX is going to be 0 because there is no other horizontal force to balance this, and then we can say the resultant is going to be equals to AY. Fine. So this is one very easy type of question solved here, and generally similar kind of questions are asked in the exam. This is the question which was asked in university exam actually, and we will solve a variety